Good afternoon, everyone. My name is Magdalena and I'm a PhD student of geodesy from the German Research Center for Geoscience in Potsdam. With our work, I will bring you to the northeast coast of Brazil, precisely Maceió, the capital city of Alagoas State, where after an intense rainfall event and a seismic shock at the beginning of 2018, many cracks appeared on buildings and roads, as well as sinkhole formations in the district of Pinheiro. After 1 year of ground survey conducted by the Brazilian Geological Service, they concluded that the main reason for the ongoing geological instability was the salt mining that was going on there since the 70s. Up to now, 4 districts are involved and have been classified as high-risk zones, and the buildings have been placed under demolition order with the consequences for more than 40,000 people who are now being relocated to other districts. In this study, we present a 16 years history of the spatial temporal evolution of the subsidence in the region using a large archive of SAR data from past and currently operational satellite missions and by applying the SBAS technique. To test the underlying cause of the subsidence pattern, we use 3D geophysical source inversion and 2D geomechanical simulation. The main outcomes from the displacement observations are that precursory deformations of 4 centimeters per year were already visible in 2004-05, displacement rate which increased up to 27 centimeters per year in the second half of 2017. The maximum cumulative displacement for the whole period up to November 2020 was of around 2 meters in an area close to the lagoon. We also provided a hazard maps based on the angular distortion value, which highlight that the area of high geological hazard does not coincide with the area of maximum subsidence. We inverted the displacement observation for a unique point pressure and rectangular dislocation source in an elastic half space using jointly ascending and descending acquisitions for the period 2015-2019, where both geometries were available. All best fit models suggest a source located in a depth coincident with the salt layer. We can notice a general increase in void reduction and an upward source migration during the year. Finally, we perform a discrete element method simulating the geomechanical evolution of 2 real size cavities. The results suggest that under both pressure, active mining conditions, and depressurized inactive conditions, the cavities become mechanically unstable, leading to fracture propagation, upward cavity migration, and partial or total collapse. If you want to know more about our work, I invite you to have a look to our recently published paper. To conclude, in our study, we successfully tracked the geological instability evolution almost from its onset, and by integrating our displacement observations with numerical models, we were able to obtain an insight about the likely source and its temporal evolution. As a general conclusion, the application of multi-temporal DInSA technique is a really powerful tool to detect and monitor geological instability, especially in mining areas. Unlikely, it is still in many cases used a posteriori and not a priori to a disaster, therefore to help emergency response rather than to prevent the hazard. I want to leave you with this drone video taken in May 2020 of the area of Mutange and Maceió that have been placed under demolition order. And now the highly populated area looks like empty ghost district.